All right, so in our next segment, we're going to start, we promised that with the whole point for introducing thermochemistry is to make these calculations more precise. So we're going to start putting numbers on calculations, thermochemical calculations right now. So we want to use the conservation of energy to relate heat and work transferred between systems and surroundings, and relate changes in heat and work to changes in the system energy. We need to look at how do we quantify change, how do we quantify the work transferred. I'm falling into bad habits. We want to quantify the work. The work is a measure of energy transferred. So work is energy transferred. You don't transfer work, you have work. And that work represents a transfer of energy from system to surroundings or vice versa. So mechanical work, this is the definitions coming straight from physics. So work is equal to minus the force times the distance. That's just from physical definitions from physics. It's you exert a force over a distance that takes energy, and that is what is how we usually quantify mechanical work. But you can turn this around and see the sort of work that happens a lot in chemical systems. If you divide the force by area and multiply the distance by the area, well, force per unit area is pressure, and distance times area is volume. So when we talk about pressure volume work, that's really the same thing as force distance work. The units are exactly the same. So the work is defined as minus pressure times a change in volume. More generally, the work is minus the integral of pressure d volume in case the pressure is not constant. We won't do calculus here. We'll focus on problems where either you just need to know a magnitude is a positive or direction, it's a positive or negative, or the pressure will be constant. So this integral just turns into a p dv. Later on, whatever your major is, you're going to see a lot more problems where you have to actually calculate a work that's by integrals. So which direction is the sign? This can be very confusing because it turns out it depends on your notation. It depends on a convention of what you're doing. So work is transferring the energy between the systems and the surroundings. So you could imagine that the work being transferred to the system or from the system, you can choose which direction is negative. So in chemistry, we care about what is happening to the system. Our focus is what's happening in the system. And so therefore, if expansion is occurring, then energy is leaving the system. So if we look at that definition, work equals pressure times delta V. If there's expansion, then the system has to be pushing up against whatever it's exerting pressure, and that work is leaving the system. So that we choose the negative sign convention. If expansion occurs, the energy leaves the system. If compression occurs, then the surroundings are pushing into the system and adding energy into the system. It's positive. You can imagine a different convention where what you really care about is what you can get out of the system. So for example, you can imagine a different convention. What you care about is the work that you can get out of the system. So the work done by the system must be minus the work done on the system. So a lot of times in physics, you pick the convention of understanding how much work the system can do. How much useful work can you get out of the system? And in that case, you choose the positive sign convention because what you really care about is the work you get out. In chemistry, we focus on what is happening in the system. And so we pick the negative sign convention. Work equals minus P delta V. So you can come up with completely consistent sets of rules as long as you obey the same convention. Again, the convention we use is work equals minus, in essentially all chemistry work equals minus P delta V, which is we care about the work being done to the system. How the system is receiving that work. So again, it's a convention. The convention we'll use in this class is usually used in chemistry, chemical engineering as work equals minus P delta V, but be aware of the other convention and you just have to make sure you understand what convention is being used. In this class, you can always assume work equals minus P dV. Okay, So that is the important convention. So let's look at this again. How do we, let's think about this pictorially. So mechanical work, you have a reaction, there's some sort of plug there that the pressure is pushing it down and it reaches an equilibrium where there's no change in the volume of the reactants and the volume of the surroundings. And some reaction occurs and it expands. So what is the work? Okay, well, the system did work. It pushed up against this piston. So therefore, it lost energy. Work is less than 0. Now let's make this quantitative. I did the back of my hand argument. So work, let's plug it in now, is minus P delta V. Well, the air is pressing in on a reaction, so pressure is positive. And the change in volume, it's positive, it's expanding. So negative times positive is negative. Negative work is less than 0. So 2 ways to think about it. The system is pushing up against its surroundings. The energy must have left the system, work is less than 0. Or just plug in, see what the change in volume is, make sure that there actually is pressure. Work is minus P positive times delta V positive, work is negative. Let's make this quantitative. I keep threatening things to be quantitative. Let's make it quantitative. Calculate the work due to a chemical reaction if volume increases from 3 to 4 liters against a constant external pressure of 5 atmospheres. Okay, so the work equals minus P dV equals minus 5 atmospheres. And it's 4.0 liters minus 3.0 liters. So the change in volume, it increases from 5 to 4. The final is 4, the initial is 3, and that equals minus 5.0 liter atmospheres. But okay, minus 5.0 liter atmospheres. We can look up the conversion factor, 0.0. But 101 kilojoules is equivalent to 1 liter atmosphere. Liter atmospheres cancel, we get minus 0.505 kilojoules, and to 2 significant digits, it's minus 0.51 kilojoules. Negative work because the volume increased. Right. All right. So thermal energy transfer. So another way that energy can be transferred is through heat. So for example, if we have 2 systems in thermal contact, if one is hot, then the molecules are vibrating a lot. They're assuming it's the same substance, then the molecules are vibrating faster. And if it's in contact through some metal wall, with a system that's colder, the molecules are moving slowly. The hot ones will rattle up against the wall, they'll heat up the wall, which will start causing the molecules inside the colder system to vibrate. So what we get is that the blue gains energy and the red loses energy. So we have a change in energy due to heat transfer. We measure the amount of energy that's transferred, that is heat. And so here we say that Q blue is greater than 0, it gained energy, and Q red is less than 0 because it has lost energy. There's another reaction that's cool that I've got a video up on the web page. The video is a little long and there's some people ranting about iron as well, but they do this particular reaction quite well. You take iron oxide, which is just rust, react it with aluminum, and you get a redox reaction that's extremely favorable. You get iron and aluminum oxide. You don't just get iron, you get molten iron. This reaction gives off 851.5 kilojoules per mole of reaction, mole of reactant. What is Q for this reaction? I'll pause. Okay, so in this case, Q is less than 0. The reaction, the chemical reaction occurs and it generates a lot of heat, and that heat goes into the environment. So it's an exothermic reaction because the energy is leaving the system and going into the surroundings. Is 851 kilojoules moles a lot or a little? See the video, I've pretty much already told you the answer to that.